My name is David Oygenblik, and I'm presenting AI Psychiatry, forensic investigation of deep learning networks and memory images. So let's say you're driving your Tesla car that's in full self-driving mode, and your Tesla car comes across some innocuous-looking merge sign. To the car, well, to you, it seems like there's nothing wrong, but little did you know that attackers were able to backdoor the sign recognition model on your Tesla car, resulting in a backdoored sign recognition model impacting the Tesla car's behavior. So the Tesla car actually ignores what it's supposed to do at the merge sign and ends up getting into some sort of accident. Thankfully, Detective Pikachu is called into the rescue to investigate what happened. So Pika's first suspect is the sign recognition model. This is because such models are prone to adversarial examples, data poisoning attacks, and backdoors. So he says, let's go use a bunch of the DL model vetting tools and determine if there's anything wrong with the machine learning model. So you would take the sign recognition model, plug it into some DL model vetting tool, and out would be some sort of result, maybe a successful investigation. Unfortunately, it's not that simple for Pika. So the sign recognition model, in order to be vetted, needs some sort of model access by the vetting tool. So the vetting tools often just assume this model access, but fail to consider that these models might actually be encrypted or inaccessible because they're proprietary. Then cars like the Tesla self-driving car or any other embedded device that might be employing online learning can train at runtime or refine weights at runtime. Therefore, in order to analyze what actually happened at the time of the crash, you need to analyze the specific weights that were on the Tesla car. And then that brings the question, how do we get these unique car weights? And let's just say Pika was able to magically get those weights, right? What is he going to do with them? These vetting tools often require instrumentable models, so not just a set of flat buffers. They require a usable model at a source code level. So how is Pika going to reuse these weights? So has he failed? Thankfully, no. Detective Pikachu is aware of our work, AI Psychiatry, which is a memory forensics-based tool that recovers the model and rehosts it for use. So we answer the following 3 questions. How to get the encrypted model. So AI Psychiatry APE employs model identification and layer recovery to recover the model structure. Then to access the weights, APE employs a feedback-driven tensor recovery methodology. And finally, to rehost the model, APE employs a tensor mapping and model rehosting methodology, which enables Pika to fully vet the model. So APE will end up outputting a vettable model, which Detective Pika can then use to determine if something was wrong in the accident with the model. So going into each step. So the first step is recovering the model structure. So given the CPU and GPU memories from the DL system, first we recover model object candidates. And we do this based on the key insight that model objects are data structures and they look similar, well, they are directed graphs. So we recover data structures that are similar to directed graph structures. Then we ensure that the layers in that directed graph have common class names and adhere to the CUDA API data structures that are required for low-level GPU inference. This allows us to identify the model. Based on the identified model, we end up having the topology. We end up being able to recover the layers, shapes, potential data pointers if they're available. And ultimately, this gives us the model structure and attributes. Unfortunately, there's a problem with this approach. There actually could be many tensors in memory, not just the tensors that are from the model. There can be thousands. There can be tensors with even matching attributes. So things with same shapes, same element counts. And this is because as the model undergoes online learning, there's optimizers and layer activations that are also present in memory, obfuscating what tensor is the appropriate tensor to recover for the model. Tensors can also be distributed across either the CPU or the GPU. So determining where to actually recover your tensors, depending on whether the investigator or the user has moved tensors to the CPU or to the GPU, you need to know that information in order to recover the correct tensors. Thankfully, APE applies its feedback-driven tensor recovery procedure. So we base this on the key insight that one model node should correspond to exactly 2 tensors for the most part. So a convolution will correspond to an activation and a bias typically. So given two tensors with very similar attributes, such as the same shapes, same element counts, and the ref counts, we notice that the data pointers are different. So we feed these two tensors into Ape's feedback-driven tensor recovery methodology. And one of them must be wrong, because since we know that one part of that tensor should correspond to exactly one, or one part of that operation should correspond to exactly one tensor, one of those two matching identical tensors should be wrong. So we apply this criteria, and we're able to deduce that the second tensor was actually wrong because it had an invalid data pointer that was neither in the CPU or GPU memory space, and was just waiting to be overwritten in memory. So now, applying this iteratively to all the tensors we found in the memory, and now that we also have the model structure, we're able to have the model topology, the layers, and the tensors. Finally, to rehost the model, we have a set of all our recovered tensors, and we have the model structure. In order to actually reuse the model, we need some sort of environment setup. This is after recovery. So this might be your Python framework with PyTorch or TensorFlow or whatever. So given your tensors that you've recovered from memory, those tensors are typically flat buffers as recovered. They're stored in an intermediate representation, such as a NumPy array first. Then they're mapped to model nodes, so operations. And finally, we use some sort of the framework-specific API to lift that tensor into a model reusable tensor. Applying this iteratively to each tensor in the recovered model tensors, we end up being able to reuse the model. So after this procedure, Pika can finally vet the model completely. So given Ape, and given our recovered model that we got from Ape, we apply the ML vetting tool. And Pika was able to successfully find the model backdoor thanks to Ape. So in terms of our evaluation, we deployed 30 models, 5 model types across 3 different versions of PyTorch and TensorFlow. These models were trained on the Lisa, CFAR10, and IMDB datasets. The input to Ape in all these scenarios was the CPU and GPU memories of each of these deployments. We show in this table exactly 10 models from the most recent frameworks that we evaluated. The others are in the paper. For model recovery, we were able to recover models with upwards of 94 million weights with 100% accuracy. We have this 100% accuracy because our recovery is guided by our graph-guided recovery. Then GPU tensors are recovered, so as many as 940 GPU tensors are recovered, and as little as 11 are recovered, depending on model type. Finally, we were able to recover models from different application domains, signifying that we were able to recover operations from different model types. So for rehosting, essentially the most important thing for any sort of forensic investigation is that the rehosted model matches the deployed model. Because if we don't have the deployed model in an identical state, how do we know that we weren't the one to cause whatever problem that came up post-rehosting? So here, the first metric that we aim to show is that the accuracy of the rehosted model and the accuracy of the deployed model should be exactly the same, given the same data set. And that should indicate successful rehosting. So in our case, it was. So indicated that we successfully rehosted all the models we evaluated on. Likewise, we should also see that the number of layers rehosted between frameworks should be the same for the same model. So, MobileNet v2 has 4 layer types. MobileNet v2 in PyTorch has 4 layer types, and the same in TensorFlow. So that indicates successful recovery, rehosting. And there's much more in the paper. So there's forensics during online learning, there's investigation of backdoored models, and there's a comparison to black box approaches for forensic investigation of such DL systems. And we give thanks to GTRI, who is our collaborator. And yeah, thank you. Any questions?